Welcome to the first Unstructured session. So now we're going to ask the question, and I hope that you will all participate. Is so what problems can we solve with traditional methods versus machine learning? Like when is machine learning sort of strictly necessary? So we just Colin and I just put together a couple of points on this Google Doc, but we hope that this will become a much longer doc with the discussion from all of you, right?
Yeah, this is just a attempt to get started. The whole point of this is that we're all going to participate. So please chime in.
Right. So I guess the first point is so when do we not need machine learning? And in fact, of course, we actually know a lot of physics from first principles, and some problems are perfectly treatable analytically. In fact, so it's desirable, and we know. We know that the solution is, and that's how we've done things very successfully for so long time. So that includes when the likelihood is Gaussian, for example. The problem is treatable with linear theory or perturbation theory. So a lot of analysis, for example, CMB and large scale structures have been done that way. Or even when the field is non-Gaussian, but the mode coupling is well known from first principles, then we can write down kind of estimators that so get all the information. And also, a real question is kind of what do we know? Yeah, exactly. CMB lancing, birefringence, all this sort of stuff. So also, what do we mean by machine learning? There are a lot of classical tools that technically are, machine learning techniques, as PCA or generalizations are polynomial regression splines, etc. we've been using for a long time. I guess what we mean these days by machine learning is something kind of fancier statistics than that, because that kind of they're kind of every physicist toolbox, and you've been using them for a long time. I don't know, Colin, do you want to take it from here? And
yeah, sure. I mean, so. Exactly. So we first tried to outline some places where things already work well, and machine learning techniques perhaps are not needed. Although, maybe machine learning can speed up even things we think we already know how to do as well. If anyone objects to this, then you should certainly start off by speaking of that.
Okay, perfect. There you go.
So
I'm on the theory side, right? So I do, and I hope I will talk about it on Thursday, and I hope to convince you that.
Would you mind using your seat mic, please?
Sorry. I hope to convince you that linear theory and perturbation theory is valid until some very, let's say, constricting limit, right? And so, and it's not just where nonlinearities are get into the picture, but very, very early on. And so I've talked about it before. You guys, right? Experimentalists. Yeah, exactly. Experimentalists give us new and improved targets in terms of very, very small targets, observables to, very high accuracy or precision or whatever. And theories need to follow suit, and they don't for the most part.
So you're worried about the inaccuracy of theoretical calculations due to numerical methods.
Yeah, so even better than linear theory, like I don't know, first order, second order, and so forth, miss the mark pretty widely. So
right.
You need to do the numerical stuff.
Sure.
And it's very, very let's put it this way, very restrictive on, let's say, MC it, right? So because it takes a lot of time, right? Computational time. So sure. It's very problematic, and I really hope that in terms that machine learning could actually pose a good solution for that.
Right. Good. This actually reminds me of something that perhaps we could have put on here, but Well, we'll come to acceleration, I guess, a little bit later. But for example, yeah, we think we understand things like MCMC extremely well, but as you note, it's very slow. And it's kind of crazy to imagine that 10 years from now, we're going to be sampling, from posterior using the same type of MCMC methods that we're using now.
Right.
Right, but hopefully we can do better. The B key is broken on your computer.
Well, it works, but you have to. Okay.
I'll let you say.
MCMC but should be improved.
Exactly, accelerated. Yeah, this reminds me actually of some interesting papers that I've seen recently from I forgot who, maybe Julian, Les Gorgon collaborators, where they're doing something that seems really brute force and obvious, which is just running class many, many times and training a neural network, which then can evaluate, linear Boltzmann calculations in fractions of a fraction of a second. And it turns out that although that's like kind of an obvious thing to do, you can accelerate an MCMC by a factor of 1,000 or something just by doing this in a clever way. So yeah, I think this is related to what you're talking about.
Yeah, that's how we are doing some of the Daisy analysis already. So kind of emulate, even just output from CAMB or from these perturbation theory codes. Because again, there's a big difference between 1 second sort of theory evaluation versus, a millisecond.
I guess maybe as the counterpoint, is this machine learning?
Exactly. Yeah, I would call it, personally, I would call it kind of traditional method, but sure, you can use neural networks to do a better interpolation, but you could have used Gaussian processes or anything. No thoughts.
Maybe we can turn to the first one of our ideas down here. So the list of items starting from here down are some topics that we thought about for areas where there are problems that we can't solve or either can't solve rapidly with current tools that machine learning might be able to improve significantly.
So yeah, of course, one of the really low-hanging fruit and that was possible with sort of the previous generation of surveys is to do a lot of visual inspection. So you have Lyman alpha forest that you want to find damped Lyman alpha systems, or you have images and you want to find strong lenses, and that typically has been done by hand. And now with the data, now that we take millions and millions of spectra or billions of images, that's no longer feasible. So things like finding DLAs in Lyman alpha forest, finding strong lenses, finding outliers, transients, anything to do with time domain, for example, that kind of becomes kind of infeasible by hand. So having very good machine learning methods, so it's certainly kind of, I think, something non-controversial that is kind of the only way to do it. So yeah, I think I don't know if that people want to add to the list, but similarly, there's even CMD by other surveys too. I've had a lot of success in accelerating some low-level data processing, doing sort of automated quality assurance, etc. So related to that, also there have been some work that we do, for example, data-intensive filtering with networks, so those are certainly some. Again, I would call probably controversial in the sense that it has been already shown to be very effective. Yeah, I guess interpolation, extrapolation, high dimensions, one of them.
No, on this automating data processing question, actually. So I'm wondering if people who work in other areas, I'm mostly a CMB person, so I thought about this example here. So with the Atacama Cosmology Telescope pipeline, for example, the way that we did things for 15 years was to have someone who actually looked at all the time-ordered data and then by hand said, oh, that one's bad, that one's bad, that one's bad, oh, there's a glitch there, and then pulled them out so that they didn't go into the map-making pipeline. In the last couple of years, we've been developing a machine learning-based tool to automate that. So so that we don't have to look at terabytes and terabytes of data by hand. Poor grad students suffering for years have been replaced by computers. So I'm wondering if people from other areas might have maybe analogous examples from galaxy surveys, for example, or 21 centimeter intensity mapping seems like a topic where this potentially is very ripe for applications. I know there's a lot of galaxy survey people here, so yeah.
Done it myself, but I think we could use machine learning for characterization of detectors, like I don't know, glitch or stuff like.
So is DES doing that? You know. Mm-hmm.
Could you use your seat mic, please?
But yeah. All right, great. Other applications. Yep.
We've done a lot of that for galaxy classification, right? So they're using traditional machine learning usually, but they do use that to help classify. And I think also for time order data. So, I can imagine that's going to be important for LSST for classifying very quickly to see whether we should follow up. And then also imagining whether we can use machine learning to fill in the missing data, especially for time order data where, or time series data where you have missing, observations.
Like in painting.
Just in painting, basically, but in time.
This really counts as low level anymore, but I know people are working on machine learning redshift determination and also like quickly getting galaxy properties like stellar masses from spectra and things like that.
Right, and there would you say that the sort of the advantage of machine learning is more the speed up, or is it just that so the spectrum is too complicated to kind of model with?
I mean, I think it's the speed up because it just, I mean, right now, for instance, in DESI, RedRock takes a considerable amount of time to go through all the different templates. So a machine learning algorithm getting a redshift would be substantially faster.
Even for spectroscopic redshift. Interesting. Yeah, I've heard about this in the context of photoz's, but not as much for spectroscopic.
Vanessa?
Actually add to this. So I think it's can be seen as like or even at a lower level, like just getting templates by using, instead of a PCA, use an autoencoder. So you just like, get a little bit of better templates, and then you can still use the traditional methods for your uncertainty estimation on top of that.
Traditional method.
This is a specific classification problem, but one that I think is interesting and sort of ripe for these techniques. So traditionally, people use the BPT diagram to separate AGN from star-forming galaxies and liners and so forth. And, you just draw a line on this diagram. And we have evidence that at high redshift, the same line and even the same sets of emission lines are not good diagnostics. So you have, sort of a clustering and high dimensional parameter space kind of problem. And it would be easy to get training data from things like cloudy models and then sort of develop a way to cluster things in a more sensible and robust way.
Would you say classification for AGN is mostly the application?
Yeah, so you can separate out AGN, liners, star-forming galaxies. Similarly, you can estimate metallicities. It's a very similar problem for metallicity estimation from emission lines.
I would also add that you can, for low-level cleanup for redshift spectroscopic survey specifically, cleanup of things like cosmic rays and like all sorts of like other things that you need to care about before like getting your final spectra out. Like you can also do those things with kind of like these like feature recognition techniques where maybe the cosmic ray is a little bit more complicated than what your template is, and you could like use that data-driven approach to clean those things up.
Yeah, sure. Yeah.
I just remember a couple of things. So like Astrophilor has done, since you talk about autoencoders, you use autoencoders to find the outliers. So you take all the stuff that you know, but then you basically find things that don't fit very well within basically the templates you draw from the autoencoder latent space. The other thing that I also want to mention is that you can use a lot of different methods to create fake noise, just like how you can create these images that like Ben was talking about earlier. You can do it with variation like autoencoders, but you can also do GANs to create fake noise for detector noise. So there's something that we do with Roman, for example. Can't, because this detector noise from CCDs and stuff like that.
Cool.
Cool. Yeah, this is great. This is a really nice summary.
All right. Anything else on this before we move on? Okay, so I mean, then of course there's the we've already kind of this is in the middle between kind of modern machine learning and so classical methods is interpolation, extrapolation in high dimensional space, and of course people have had a lot of success with using machine learning techniques to do this more efficiently. So that's sort of great to see that our toolbox is sort of rapidly expanding. Does anybody? I mean, I don't think this is very controversial, but does anybody have sort of comments or so want to reinforce or your favorite method that you thought some interpolation was really too hard or too computation expensive, and now machine learning really solved your problem?
I'd be interested to know the highest dimensionality.
Can I? So for interpolation, for sure, but extrapolation.
I mean, that's extrapolation is always tricky whenever it comes to physics. But I mean, it's kind of the same, often the same algorithms that can do both. And then you of course have to be a little careful in terms of validation. Extrapolation is, even with classical methods, right, is a dangerous thing. So you should keep the caveats in mind, I guess.
I have a comment on this high-dimensional space problem. So I think, although there are many wonderful applications of it and very nice performance, I think still we kind of often lack the understanding of why it works so well in high-dimensional space. Especially like in high-dimensional space, the functions are complicated, right? So we should not expect that there's a miracle thing and we just machine learning can solve all this complicated problem, because intrinsically it's a high-dimensional problem. So then I think the part missing is why machine learning can do so well. What is the assumption? What is the information it uses to kind of converting these high dimension problem equivalently into some low dimension problem? I think so that's something really will be interesting, and also that can kind of explain why for some particular application it works well, for some others it actually does not work well. Just people don't report all the failures. but yeah, I think it'll be nice if you have some understanding to be able to explain those results.
Yeah, I think this also connects to Paco's comment about being wary of extrapolation. If we don't actually understand why it works so well, or sometimes why it doesn't end up working, then we should certainly be wary of extrapolating.
Yeah, and personally, I think actually many times it's related to some intrinsic structure in the signal. So still, it's because the signal itself is actually a low-dimensional object. It's just it happened to be live in a high-dimensional space, but there are intrinsic structures, and kind of the machine learning by its architecture kind of reduce the dimensionality.
Yeah.
One thing machine learning is very, very good at, right, is pattern recognition. And I know of some works that, well, instead of recognizing the pattern and say that something fits the pattern, looks for something that doesn't fit the pattern. Now that's something that's very problematic because you don't know what that something is, and so you're reduced to setting thresholds on, you know, how similar this is to the data and so on and so forth. Would be great if we could find some, you know, self-imposing algorithm that will be able to classify what is an aberration.
So this goes into sort of it's you would say, is it you know, a kind of generalized outlier detection? So you want to see not only this looks different from the rest of the data, but why does it look different or something? But
not just you know, different, but yeah, how different?
Right.
What type of different?
Yeah.
Yeah, I think this connects onto some of the transient detection.
Yeah.
That was mentioned by Shirley and others earlier. I don't know if there's any LSST transient people here, but my impression is that they're going to very strongly rely on these types of methods to hopefully find interesting new stuff in the LSST data stream, which is exciting but also scary. I mean, also at the LHC, I mean, I don't know if we have anybody who's worked on LHC stuff here, but they certainly can't save even a fraction of the total data stream from CMS or Atlas. So they rely already on these type of machine learning outlier recognition tools to look for events that don't fit the standard model template.
Yep.
Yeah, who knows? Maybe we've just missed new physics at the LHC because one of these algorithms didn't perform as well. So, that's a scary thought.
So yeah.
While we're on the topic of anomaly detection, there's a lot of people working on that for detecting anomalous spectra in, for instance, PFS. So I think that's also a nice machine learning application.
Cool. And yeah.
Hello. Yeah. So I think the way I like to think about most of these machine learning models are, in fact, they are really just interpolating functions, right? So whether you are estimating density or making regression or something, you are just basically trying to find the mapping between input and output, right? So basically in all of them, interpolation, basically. For the extrapolation, just to give an example, I have seen one paper where they have done is that they tried to predict what is the luminosity function for AGN at high redshift, and the way they did that is to look into to try to find the mapping between all the galaxy properties and the AGN in these galaxies, and then try to predict that at the faint end and see whether that. Of course, we don't have the telescopes to see that by the faint end, but this is one of the applications that, and it looks like roughly to other models that they can match the faint end of the AGL luminosity functions. They kind of getting something close to that. So if you are able to correlate between all the properties between galaxies and whatever, you could in fact extrapolate. But that's the question. Also, we don't know whether that's true or not because we don't have the measurements at that site. But somehow it could have the potential to extrapolate too.
Right. And so related to that, on Zoom, Gabriella says that deep learning, at least if we mean, so machine learning we mean deep learning, then it's not by itself so made to extrapolate, but yeah, and of course, you know, as you say, there's you know, some potential there. However, yeah, there's some potential there, but the usual caveats. I think it's true in kind of most of physics that extrapolation is very dangerous thing to do.
Well, I think it's one thing to extrapolate when you think you know the physical law that you're using to make the prediction. Right. But if it's based solely on recognizing a pattern and you don't actually have an underlying physical understanding of why it exists, then I think it's super dangerous. Right. We should always keep that in mind. Sorry.
So let's go to Vanessa, and then we should take some questions from Zoom.
Yeah, I'm not sure if it was mentioned already, but it's not on the list. So related to interpolation is data imputation. So basically, if you have corrupted data, denoise it, or you know, infill masked areas and so on.
So yeah, so this is kind of a
oh, you already
really along this theme. So like here we were talking about filling in a missing data in the context of say time ordered data, some like
yeah. So I mean more on the like image level, yeah.
So image level, yeah. Okay, so both can we say both in space and time or something? Time.
Has anyone made a CMD in painting tool based on machine learning methods?
Oh, I mean, I'm sure it's Wiener.
I mean, the Wiener filter is the
that's kind of the optimal. Yeah. Perfect. Then maybe now it's a good time. So I've seen, you know, there's a little bit of chat on Zoom. So if remote participants want to contribute, maybe now it's a good time if you want to raise your hand, and we'll see if we can connect the audio, hear you.
Yeah, the EV can do it.
Okay, perfect. So if you can just raise your hand, you know, we'll move on quick soon. But at any point we're kind of monitoring that. So please do contribute, and you know, if Gabriel or others want to sort of jump in, that'd be great. Okay, so I don't know. I don't think I see. I don't see any hands raised for now, so maybe we can move on. But please do it. Feel free to jump in anytime. Okay, cool. So then yeah, shall we move on? So
I think we had reached
accelerating
here.
Mm-hmm. Yep.
Yeah. So I think that these next few topics connect onto things we've already heard about that we're going to hear more about later today. So presumably everyone here has lots of thoughts on these ones. So first up, accelerating simulations is obviously a big topic here at the CCA. I'm interested to hear your thoughts from people working on this problem.
Right, and yeah, maybe a related question is how do you know that then your sort of accelerated simulation is good enough? Like what is it? So you know, what was, in other words, what's the end goal? So you know, is there procedure? Is you want to have an accelerated simulation that reproduces the universe as well as possible, sort of all aspects, or do you usually, you know, restrict yourself as like, okay, let me make a simulation that has variance and has the right power spectrum, but maybe, you know, it doesn't have the right 5-point function or something. So at what level, you know, what level of sort of validation is needed, or what do you hope to achieve? Sort of question. I mean, we've heard some talks this morning.
Yeah. So maybe even one step back. I mean, this is a little bit crazy. So I think like 2 weeks ago, I was giving a talk in a workshop that it was called Philosophical Aspect for Cosmological Simulation, like something super weird.
Okay.
And we were talking about
philosophy, like
we were actually talking with philosophers, and one of the philosophers, the conclusion of this guy was that the kind of simulation that we run in cosmology, this is a kind of very, very low level in comparison with other fields. We never do validation, we never do verification. And it is that, you know, validation in our case is incredibly hard. You know, even what is the impact of the softening length on your simulation. You don't have a conceptual model or something like that. So even from the standard simulation that we run, there are problems. So I think here we will kind of have to deal with the same ways. But usually, the typical verification test that we do in order to check the simulation is probably something that we can do here, right? Are we going to trust the simulation to compute the endpoint function that we haven't validated before? Probably you cannot do that, right? So, but you can always check with your reference one.
Right. So you're saying that in a sense the validation is problem specific, and you should go hand in hand with sort of the analysis you hope to do with those accelerated simulations.
Maybe my counterpoint question would be then, what's the point of the accelerated simulation?
To save time, I think, which is...
what are you going to get out of them at the end? You're saving time running a calculation, but what's the point of the calculation?
I mean, I think at the end of the day, you want to marginalize probably over all these things, right? Like you want to marginalize over astrophysics or even, your softening length, resolution, all the possible things. So if you want to do this brute force, it's going to take a very long time. And also, I think you can show I think it can be shown that if you have bugs, even in your simulation, if you have many different codes, basically, and you train a neural net, the neural net will be robust to bugs that for sure there are in all the codes.
Right.
So, yeah.
Yeah, so I think beyond just the idea of how we validate simulations, another kind of parallel idea could be, can we design models that make use of all kinds of these multi-fidelity models that can make use of simulations that are not exactly accurate, and that essentially balance computation and accuracy, and somehow given a family of simulators that have different trade-offs in terms of accuracy and speed and maybe accuracy in different places, can kind of query them intelligently and make intelligent use of a fixed amount of computational power to give you the best kind of inference that you can get from a set of simulations you get. And in that sense, maybe the goal is not to create, simulations that are as accurate as possible, but rather create kind of a family of simulations that are accurate in different ways and that are fast in different ways, and design on top of that models that can kind of make use of the fact that it is given this set of simulators that have different characteristics and use them intelligently to perform the best possible inference.
Right. I guess a corollary to this is the idea of developing sort of like a multi-scale set of simulations, which reminds me of the SMOG collaboration project here. Yeah.
Sorry.
I had was, one thing that machines are really bad at is basically applying heuristics, right? And then could we not, integrate different heuristics into machine learning algorithms or so on? Kind of similar to, I think, Miles did that work, or of let's say, finding the right Lagrangian, let's say for a particle self interaction or whatever, right? It has to have the right dimensionality, it has to have the right symmetries, and so on and so forth. So, these are kinds of considerations that we make seamlessly. Can we make the machine learn how to apply these? Maybe. I don't know. It's kind of far-fetched, but maybe.
Yeah. So we have three, Vanessa, and then
Yeah, I mean, maybe that's also related to what Paco already said. So I think there is, generally we have this problem that there is, all simulations, they don't look exactly like the data. There's some distance between the simulations and the data, and this will be true for traditional simulations, and this will be true for accelerated simulations with machine learning. So I think there is this question of how do we measure this distance and how do we, how do we overcome this? And I think it's, I mean, this is a problem in machine learning in general, and I think that's something where we should also be just monitoring what the general machine learning research does, because it is known that you have a problem with distributional shifts, like between your training data, and if then you apply it to some data that looks a little bit different. So I think this is a hot topic in machine learning, and that's something where we definitely need more research. But I think, I think that's one perspective, the kind of perspective that we should be taking when we look at simulations and accelerate simulations.
Accelerating the simulation, I think of it as more like emulating the behavior of the current simulations, and I think that's very important now, even if they are not really correct. I mean, people going on and just developing more models and accurate models, but it's good in a sense that you can. It's not only it's fast, but at the same time you can explore large scales very easily, right? Like imagine even if you want to combine a simulation where you can resolve multi-scales, right? Like you want to resolve the ISM and the CGM and the IGM together from parsec scales up to gigaparsec scales. And if you are able to accelerate to take these emulation for different scales and combine them into a very large box, you can only do that with machine learning with the current computing capabilities, unless quantum computing comes, and that's another.
Yeah. Exactly. Quantum ML is a big topic. Yeah, exactly. And the Chang?
Sorry. I just wanted to say, like, I think when it comes to using machine learning for accelerated simulation, sometimes the standard for it is higher, or like the what people are comfortable with tends to be higher than other methods. Whereas, like, we're happy to use perturbation theory even though we know it's inaccurate up to a certain scale, and we're like, yeah, we'll just cut out those scales.
Well, it's because we know how to calibrate it so precisely, right? I think we know how to calibrate it.
But there's also observational systematics that we think we have control over. But I think these are all kind of, this is not true. We don't have a perfect measurement. So I don't see why we need to have a perfect acceleration for machine learning. So I think it just has to be good enough. And as long as you quantify what enough is, some level, I think that's fine.
Yeah, that's a very good point. It also connects nicely onto our next
topic. One second. Still, we have a comment from Ben Horowitz in the chat. But Ben, do you want to speak up if you're connected? I don't know if the audio is. Okay, He says.
Oh, hey. Oh, sorry.
Oh, yeah, perfect.
Yeah, sorry. So again, my comment was just that I think that in terms of accelerating simulations, I think there's kind of a whole sliding scale, right? Where you could use things like, the CAML simulation suite to train a model, where you could just plug in your cosmological parameters, generate a whole simulated volume, and extract whatever summary statistics you want from that mock generation, things along those kind of approaches. Or you could use a traditional method to generate the same kind of emulator set that you would with that kind of method. And so I think that kind of as you get closer and closer to new discovery, you should kind of rely more and more on the traditional methods. But I think that the accelerating simulations could be really great for kind of constraining things close enough so that way when you are generating, say, an emulator, you have a much smaller region of parameter space to investigate. And if for whatever reason something's wrong with your accelerated simulations, you'll at least have a check at that point, right? Where, oh, well, we thought from our, generated emulator, we thought we were in this parameter space. But at least when you then go to do the final check, we're actually doing a traditional emulator in that certain constrained region. Hopefully, you would then see, oh, well, there is something wrong with the machine learning method. I guess philosophy of the simulation itself notwithstanding.
Right. Yeah. Cool. Thanks for the comment, Ben. Yeah, anybody else remotely also, feel free to speak up or write in the chat, and then if you can't. All right, maybe we should. Oh, sorry. Yeah, please.
I think one of the main points of how we can validate how well the network is, like how well it's emulating, can be the generalization to the other kind of universes.
Because I personally feel that the era of training on a particular kind of parameter simulations and then testing on it is kind of saturated. So what we need to focus more on is generating the models that will generalize well on a very drastic variety of cosmologies. So if we are testing on one set of parameters and we're training on it and testing on it, and then we are using it to generalize on like a complete, like let's say a Latin hypercube kind of simulation, because that's what we kind of did in our project, then one of the validity of the model will be how well it performs on that generalized set.
Absolutely. Yeah,
something. So machine learning, we know that is really good at it, like reproducing the mean relations, right? We lose only is the scatter, right? So if you don't care about the scatter much, right, because this is just the variance we always use, we don't really, even if you use like all these density estimation, you don't really get the scatter right, but you get the mean relation right. So if you care only about the mean relation for some physics or at a given scale, then it emulating the behavior of that mean and doing that would be okay, even like if you want to do a large scale or do something else. So it depends on about capturing the variance or not for the given data set.
great. I think we have about 5 minutes, so let's quickly move on to the last couple points here. And I think our last point is very closely connected to the topic that Zoltan is leading a discussion on later today. So I suspect we'll come back to some of those points later. Okay, so I guess forward modeling of systematics or observational effects is something we've alluded to a few times, but haven't gone fully into detail. We heard some about this from Cheng in his talk earlier with the fiber collisions. Interested to hear about other examples that people have.
Exactly, like fiber collisions are a kind of perfect example that are hard to treat theoretically, because your weights are density dependent and they're non-Gaussian, depend on the underlying density that you don't know, but they're kind of infinitely forward modelable. So that's one example where it certainly makes your life a lot easier. Is there any other similar example? Yeah.
Example I can give, like work with a collaborator, Mehdi Rezai in DESI. So if you're familiar with like the legacy surveys, it's really a compilation of like 3 different imaging surveys. So the imaging properties, for example, of the maps are very different. And with like projects where people are trying to like combine multiple data sets together, where you might have different variation in your observational properties, like how do you figure out like what the imaging systematics of your like these like new maps are that are being produced by combining different surveys together is a challenge, because in many cases these are there are like a lot of like non-linearities that you just can't regress out using linear regression. So I know like the Mehdi, for example, has been using like neural network based approach to kind of like model like how can you combine different surveys. So I think that is like one good example as what we're trying to joint efforts. This seems like a nice way to be able to like model like those issues that might pop up and normalize it across board.
Yeah, absolutely. I mean, yes, so some of these problems become definitely a lot easier using these tools. And okay, sorry.
Sure.
To your answer, do you expect your method to work for things like joints, space, and ground, or not?
Could you?
I'm just wondering because you're talking about these legacy surveys where you're combining different probably ground observations. I'm curious, do you expect this to work for like ground and space combined? So I was thinking about Ruin and Roman or Euclid.
I will answer with the caveat that Mehdi Reza is really leading that part of the effort. So right now, the focus of our work has really been within the legacy service itself. So because you have the DES footprint, then you have the BAS MZLS in the northern side, and of course if you look at any DESI imaging map, you can see that the DES footprint is very well observed. The thing is very different. So I think the idea is if we're able to convince people that this works for a survey like this, then perhaps in the future we can start to think about maybe extending that into combining space versus ground and those kind of.
So, yeah, maybe this isn't an entirely fair comment, but I do feel this is actually an area that's a bit more neglected on the ML side. There's lots of papers doing things like applying a CNN to a simulation and getting good constraints, but actually doing it on real data where the data does have, weird things in, just that, scattered light in the telescope or ground pickup and these sorts of things that might play havoc with some of these sort of methods that do very nonlinear transformations of your data, and studying how those effects propagate through and making robust methods to those things, I think is a little underexplored at the moment.